Good morning to all the participants. So once again, welcome. I welcome all of you to the first session of day 2. Now with us we have Mr. Jairam CV, uh, uh, the speaker for the first morning session. Now I'll be very briefly introducing his CV to all the participants. Now Jairam CV, sir, he has experience of more than 16 years in the areas of GIS, remote sensing, and spatial data conversion, and MLS data pre-processing with sound knowledge of navigation data, both in marine and road. Now, at present, he's with Topcon Sokia, India, as Assistant Manager Technical Support. So, handling high-end products like mobile LiDAR, static LiDAR, GNSS, along with software solution of Topcon for southern region of India. Now, he has a very wide areas of expertise. Now, he has expertise in GIS software for creating GIS map and map databases, and image acquisition and processing and geo-referencing, GPS technologies and pre-processing, handling DGPS surveying, image analysis and interpretation. Now, sir has also worked with many other organizations. Now, currently he's with Topcon Sokia India Private Limited at Hyderabad. Now, earlier to this, he has worked with Census Technological Limited at Nagpur. Now, he had held a key responsibility mainly in production management, client management, and project execution activities, along with vendor management as well. Now, with this, I welcome Mr. Jairam CV, sir, for this session.
Thanks, Sharon. Thanks for that lengthy introduction.
Okay, so over to you, sir. You can take over, sir.
Yeah, thanks, Sharon. And thanks for providing me this opportunity to showcase in this August platform. So with this, without further delays, I will take you through the presentation for today's, which is on emerging modern surveying equipments, modern surveying techniques. So let me stop my video because of uncertain internet connectivity issues.
No issue, sir. That is all right.
Yeah. Hope my screen is visible and I am audible to everyone. This
everything is clear. Everything is clear, sir. Presentation is also clear.
Yeah. So this topic assigned to me is like emerging techniques in modern surveying. Before starting this, I would thanks to yesterday's speakers, Professor Dasarath Kolur sir, and my fellow colleague, Mr. Chandra Mohan, who has already used my presentation, where they have already covered up most of the things in regards to that topic of this particular event. So today my agenda would be like we'll discuss on basics of surveying and emerging techniques in modern surveying. So it's like overview of the surveying. Most of them are aware of. Still, we'll just go through this basics so that it will be like a refresher sort of thing. What is the surveying like? The whatever it's like measuring the specific surface of the earth. This can be finding out. Hello. Hello. Sharon?
Sorry, yes, sir.
Yeah.
Sir, pardon me?
Hello.
Sir, we are not able to hear you.
Hello. Now?
Oh, yes, sir. Yes, sir.
How is it? Yeah, sorry. Sorry for that. So the primary aims of the field of surveying is to measure the horizontal distance, vertical elevations, and relative directions. So what is the vertical? So what is the relative and absolute directions? So as mentioned in the figures, the relative directions are measuring uh, with respect to the current location and orientation of that object, which we are all known as a relative direction. And absolute direction is the exact place on the earth where we are standing. This is generally termed as latitude and longitude. So we use this surveying in many applications, like in day-to-day activities of boundary surveys. You call it land topography. You call it river surveys and the delineation of corridors for the many wide usages of construction of roads, tunnels, airports, and pipelines. Uh, Basically, in boundary surveys, what we do is we'll take in satellite imageries and we'll delineate that particular boundaries by imposing that cadastral data onto that, and we are and demarcating that particular lands, which in today commonly government of India has also floated and program for NLRMP, that stands for National Land Records Modernization Program, where this entire cadastral data has been converted into digital maps by using different surveying techniques, like few of the states are using remote sensing, and few of them using the codes using GNSS. And hope everyone are aware of land topography maps required to prepare the detailed engineering designs to flow to get the flow analysis. And the river foundation surveys are used to have the proper passage for the ships which are incoming and outgoing, to remove the excess sand. That's the process called dredging. And basically, this roads and tunnels expansion and formation of the new roads by using the different survey techniques. We use this. We used different type of surveys for the different applications. So previously, what we are doing is conventional surveying techniques, where we used to do like page measurement. Page measurement is nothing but the people are walking with the foot, and when uh, actually the one normal walking step will have a 0.75 meters, or it could be a 30 inches, and if or a double step, returning to the same foot approximately 1.5 meters or 60 inches. So like that previously, like what we used to do, like page measurements, and most of them are used chain, tape, steel, enforced vinyl type. Uh, by modernizing and combining of different engineering platforms, today we are at the platform where we use the modern surveying equipments, today we will be focusing on automatic level electronic theodolite total stations and global positioning systems, lidar and UAVs. These are all will I'll walk through the case studies which we have already done it in real time, and we'll focus more on the techniques, not going deeper into the subject. As anyway, this has been covered by covered uh, by the upcoming speakers in their detailed presentations. So so the different type of surveys will be taken as per the application and as per the accuracies which generally people used to have. So for an accuracy of having 0.5 to 2 centimeters absolute accuracy for the engineering surveys, basically we'll use total stations, GNSS, and 3D laser scanners. And For survey construction mapping as well, where we expecting in 5 to 15 centimeters of absolute accuracy. We'll be having mobile mapping systems or a GIS, where we collect GIS data collection by using again GNSS, and on the satellite images we superimpose this data and we collect this all those information and we present it to the required things. And the more the range, the less the accuracy. For having 1 meter or 1 meter absolute accuracy, we will have an UAVs or UAS, that is unmanned aerial systems like drones, where we take a photograph, photographs, and these photographs again taken into photogrammetric technique, and we extract digital elevation modules, digital terrain modules, surface, contours, etc. So first we'll see about levels. Leveling survey basically still, though we are using all the modern equipment like GNSS LiDAR, still for establishing the control network and to have an geodetic control, still we are using this auto levels to have an vertical control. Basically, this vertical control still people believe in doing with auto level itself. So by using this auto levels, we'll create this first order leveling benchmarks, and we'll have that MSL mean level heights by using the geodetic corrections. So where we use this leveling is basically we will use to get the height of that particular terrain. What we say it could be a road or it could be in any construction site where we require this height. So like I said, in the various construction works or the bridge construction, the level should be in the same height. For that purpose, we'll use our auto levels where where all the pillars will check that whether it is in the same height or not, to maintain the certain heights. And while installing the pipes and constructing the ducts to maintain that particular slope where the flow has been designed for slope setting of that particular drains, we use auto levels again. And even for the deformation studies also, where we can constantly monitor a particular piece of line periodically, where we can have this information of particular area deformed. We can have that we can use this auto levels for the deformation studies too. So moving to electronic theodolite. So yesterday uh, uh, Professor Dashrath sir has made clear regarding this electronic theodolite and EDM. So basically, electronic theodolite, what Topcon is offering, will have a EDM inbuilt with this nowadays. So where the electronic theodolite will have options, will have an options to measure horizontal angle and vertical angle. Along with that, we can measure the horizontal distance, uh, like there is an instrument which transmits an infrared rays, and it will be gets heated to the reflector, and that reflector light will uh, travel back to the transmitter. There the microprocessor calculates uh, time travel, so that uh, particular slope distance or horizontal distance will be given on the screen itself. So there are two types of electronic theodolites. One is like optical type, where we can have that protractor pattern directly, protractor which we have used in geometry box. In that pattern, we can read the display on the instrument itself. And second one is digital type, where we can see that particular horizontal and vertical angles directly on the screen itself. So the core subject of today's particular of this entire theme is like total stations and rows. So we'll focus more on the total stations. So yesterday sir is explaining like how it was like I try to give a pictorial representation of how total station works when we fire an infrared laser beam and a reflector is mounted. A reflector is nothing but a prism on the stadia rod which a person will be holding, or it would be kept as a stationary for to measure that particular area. When when we set this infrared rays, it will directly hit to that particular prism, and it's comes back to the station. There it's calculating the beam reflection, and it will give the particular areas horizontal distance and angles for our design purpose. So what types of total stations are there, and based upon the different type of applications, the total stations will be vary based upon the accuracies also. So there are basic type and non-prism type, Windows CE type, motor driven type. Motor driven type are nothing but robotic total stations, and imaging type, monitoring types. Monitoring types are very precise ones where we use for deformation monitoring, for dam structure monitoring, for any construction activities which is happening besides where we will be requiring this monitoring to avoid any misshapes of falling that entire structure. For the types, we will be using monitoring type, which is very precise one. So, what is angle accuracy and distance accuracy? Distance accuracy, when we say 1 second, 1 second is a 1 mm at 200 meters. So 50 centimeters at 100 kilometers away. When we say distance accuracy of 2 mm plus 2 ppm, ppm stands for parts per million into distance. This is if we roughly calculate 4 mm at 1000 meters. So we can add that. We can add this into the distance which we have covered. Where will have this distance accuracy? So typically this prism mode where we use for power pole, guardrail and fence, and for demarcating the boundaries, we'll use this prism modes. So yesterday there is a question regarding what is the advantages of having Windows based TS rather than having a Linux based TS. So I try to put some pictorial and a brief about that one. So the functionalities or the advantages of having a Windows total station is we can calculate the we can have a calculate function on board, and we can create a surface contours and volume calculation, and we'll have an advanced loading functions, and we'll have a surface takeout in the field itself while having the background of surface, and we have a traverse adjustment on board, and there are vast library to import and export formats it will support for IFC, and it will support AutoCAD as a background, and we'll stake on that particular road. These are all the additional functionalities of having a Windows total station. So for a case study, we'll see that volume calculation in an electronic total station as a case study. So I have surveyed this all the points for doing a volume calculation on board. I am doing it on the on board, nothing on any office software. So I taken this all the points, and I have assigned this codes. So these codes are like base bottom and top bottom. in order to generate a surface, in order to calculate in volume, we will be requiring two surfaces. So for that reason, we taken like this, and this has been assigned like base bottom and top bottom. I just assigned this in the code while doing the survey. And what I will do is I will just quickly run through a video where we can, uh, yeah, we'll show you how to calculate this particular volume calculation on board in the field. So these are all the options where we can have on board. Like we are creating a volume, and we are adding the points by code. As I mentioned, the bank bottom I have already taken and created as an bottom surface. And again, I am going to give another surface which is top surface. And for that, I have already taken this set. I have already assigned like TB, so it's automatically fetching with the help of the code which I assigned in the field. So now I created both the uh, both the surfaces. My surface has been generated. You can see the volume along with the contours, which is in the intensity view. So this is my original surface. This is my bottom surface. So if we can have an surface volume in the field itself. You can see that fill is 3,138.299 cubic meters of fill needs to be done in this particular area. So again, having an advantage of another case study of having a Windows total station while working with the raw data. Sorry. So while we have a design file of that particular chainage of say 45, excuse me. Sorry for the interruption. Sorry, I need to take an urgent call. So sorry for that. So when we have this particular chainage of 45, and we need to stake in that particular chainage, what we do is we'll simply ask our field team to send that particular chainage to us, and how they are going to send that thing also we'll going to see in my next upcoming slides. So once we receive this data, we import this data as a drawing into the total stations. And once we inserted this particular chainage as a drawing, we can stake this data based upon our like on that particular berm edge and toes like this. We can stake. We can have this original design data in our TS where where we can check the cut and slope in the field itself. So as I said, we'll have a vast library of import and export formats. Like we'll have a layout for while we are doing the layout, we can have a drawing as a background, and we can have this in the field to avoid any further confusions. So we can have this IFC data. IFC is nothing but BIM data where we can have this as-built drawing files and IFC data too. And we can ask our team persons to seamlessly connect. Once we did once we complete the survey, we need to send this data, and for that we need to download the data. We need to connect it to the laptop, or I mean, first of all, we need to connect an USB or any or a, I mean, to the COM port, and the data needs to be downloaded from the total station and back to the laptop, and from that laptop we need to send it to the field, to the office. To avoid such I mean, in that case, there could be probable chances of error while we are sending in different files rather than the intended one. To avoid such confusions, we have a seamless connectivity option of having a Windows TS, where we'll have an office to field connectivity, that is like a Magnet Enterprise, that is a cloud-based platform where we can send the data to field and field to office. This is seamlessly connected. So in order to avoid the more confusions in the field, because if we if we hand over some data to design team, we are not sure that particular data will reach to the field in the same manner. So to avoid such confusions, we can have this enterprise, and this will be enabled while we are having this Windows based total stations. So I would not be more into manual total stations. We'll move into robotic total stations. What are the advantages of having an robotic total stations? So there are a few functions of having an robotic total station. One is like auto collimation and auto tracking. I'll show you how the auto collimation function works and auto tracking works. And before that auto collimation function, I'll justly, I mean, I will roughly brief you. Whenever we are doing a total station survey, the prism needs to be bisected at the center of the prism. Then only you will have a perfect reading. So for that, the surveyor needs to strain a lot. There could be an eye fatigue cases, and it's a time taking process too, and there could be a probable uh, manual errors may prone. So to avoid that and having an advantages of having robotic tool station, what auto collimation function does, you need to roughly sight the prism, and it will does its job. So it will directly find accurate center, so that our job is very much easy and we'll have an accurate data too. So next, like this. So what is an auto tracking? This auto tracking, while we having this auto collimation function, once we lock here, once we need to bisect the prism and lock the prism, and the robot will track you while we are moving. So these are the advantages of having robotic toll stations. So a small video of comparison, like what we have discussed, like of auto collimation function versus the manual total stations time. We'll see that time elapsed here. Person is doing an person is assigned to take five readings here. In the left one is auto collimation robotic total station, and right one is manual total station. And with the auto collimation function, this person is already finished his job where this manual guy is taking his time to finish because he needs to adjust the horizontal vertical angle and he needs to look into the telescope again and again. So finally he finished. If we see the time comparison, it was like 1.5 times faster than the manual total stations. So this is an auto tracking function, a small video again. So while having this auto tracking, once he logged the auto tracking prism, he will automatically take the topography points and the person needs to do only uh, shoot the trigger button, while the manual person will have this I mean he needs to do horizontal vertical angles and he needs to look after the telescope and he needs to press that trigger button in order to take that particular point. So again the comparison goes like, so he almost finished in a very less time comparing to this one. And to show the auto tracking capability of the robotic tool station, how fast it will track you. Like this total stations are having 180-degree seconds tracking speed, yeah, rotations per second, and having an see wherever the guy is moving around, it was following him, and the prism is not getting lost. So these are all the few advantages of having a robotic tool station. So as I said, the very precise one, what are the advantages of having monitoring total stations? So we'll have an uh, this is 0.5-second accuracy monitoring total stations where we use for displacement and deformation monitorings. And when we when we are discussing about deformation monitoring or displacement, there are multiple targets has been kept upon, and this monitoring total stations needs to automatically check that particular all the prisms, and it should not take the which is near to the telescope, and it has to taken in a particular pattern to do the analysis for that for the software to get that accurate deformation monitoring results. So it's need to it has to check in the particular format, and it should not check like which is near to the telescope. So in a standard TS, what it will do is like which it will check the prism which is close to the instrument. Like, see, this is not the correct prism search for the deformation monitorings because there are multiple prisms has been assigned. So what is the correct pattern to check is like it needs to check the far prism, then that which is closer to the telescope. So these are all the few algorithms which has already been assigned for the monitoring total stations, which is very precise in nature. So another like it's an there is another algorithm to check the multiple prisms. Like this is a pre-scan algorithm where we take a case study of a particular dam. We assign this all the prisms at a particular at different locations. So it will automatically search as per the algorithm which we set, and it will send the results periodically. Like if we ask that robot to track in a uh, track in a particular time period for say an example of 30 minutes or 1 hour or 12 hours, it will directly trigger that particular algorithm, and it will have that all the station data, and it will send data to the software to calculate this uh, all the location data such that that deformation monitoring can be monitored. So especially where there is a low light, uh, this function, this is another beautiful function where that inside of the tunnels there could be an no light in some cases. So this is the function where we have a target illumination in the tunnels. When we do a uh, when we switch on this particular illumination in tunnels, uh, that prism sheets which we have already taken, it will illuminate, and we will have an option to continuously ask it to blink, so that it will be easily identified and it will be easily measured. So another function of having an update rate. What update rate? What we have seen is like in the previous in the last video which we have saw, the robot is tracking that prism. So for the tracking prism, the position need to be updated periodically to the robot, such that we'll have an access to see on our monitors. So earlier it was like a position update rate of 2 to 3 hedges. Now the latest position rate which is came like 10 hedges. I request to please look at both the screens simultaneously. See when we are having a low position rate, the prism is moving like this, and when we are having an high position rate, it was moving like very smoothly. So these are all the few updates